So the ocean affects climate by storing and transporting huge amounts of heat and carbon dioxide. And so if we want to understand how climate's going to evolve in the future, we need to know what's happening in the oceans. About 90% of the extra heat energy that's been stored by the Earth's system over the last 50 years is in the ocean. So when we talk about global warming, we're really talking about ocean warming in a real sense. So one of the main goals of our work in the Southern Ocean is to measure exactly that. How is the ocean changing? And to learn how ocean changes might affect things like climate, sea level rise, and biological productivity. The Southern Ocean is a really important part of the ocean to study because it's really unique in a number of ways. First of all, it's only in the Southern Ocean that there's a band of ocean that circles around Antarctica that's totally unbroken by land. It's a continuous channel of water. And it turns out that the dynamics of the ocean currents that circulate in that channel are very different from the rest of the globe. It's the home to the world's largest ocean current. It carries about 150 million cubic meters of water every second from west to east, south of Australia, between Australia and Antarctica. And that connection between the ocean basins that's formed by that current transforms the whole global pattern of ocean circulation and also affects global climate, not just the climate of the Southern Ocean region. That strong current, one of the things it does is prevent heat from spreading from the relatively warm northern latitudes further south, and so it helps contribute to the icy glacial climate that Antarctica experiences today. It also has a big impact on Australian climate because it affects the weather systems that come across the continent from the south. So our weather in Australia is largely determined by what happens in the oceans around us, either the Pacific, the Indian, and the Southern Ocean for the southern part of the continent. Another thing that makes the Southern Ocean very different from the rest of the ocean is that it's one of the few places, or the only place, where water that's at depth in the ocean, 3,000 or 4,000 meters below the surface in most of the ocean, rises all the way to the sea surface in the Southern Ocean. And so it's the only place where the atmosphere connects to the deep ocean, and that has a lot to do with how much CO2 remains in the atmosphere. In today's climate, the Southern Ocean soaks up, the oceans as a whole soak up about 25% of the CO2 that we emit. So if it wasn't for that, the ocean acting as a sponge, climate would be changing even more rapidly than it is today. The Southern Ocean is particularly effective at storing CO2. So about 40% of the carbon dioxide that ends up in the oceans enters through the Southern Ocean, and it's because of this very active vertical circulation where water sinks from the surface down into the deep sea, and also other waters rise to the surface. And that interplay of rising and sinking motions has a large part to play in determining how much carbon dioxide remains in the atmosphere. That vertical circulation pattern is only found here. There are other places in the ocean where water sinks to the deep ocean, in particular in the North Atlantic. But the Southern Ocean is the place with the most active exchange between the interior of the ocean away from the surface and the surface layer of the ocean that's in contact with the atmosphere, including the carbon dioxide that we're pumping into the atmosphere. What we're here to do on this voyage is to, there are 3 or 4 main parts to the voyage, but basically we're looking at how the Southern Ocean is behaving today, what the temperature, salinity, oxygen, carbon dioxide levels, what organisms are living in the sea and where, and relating those distributions to the ocean currents, and also comparing what we measure today to measurements we've made in previous decades. Work we've done in the past has shown that one of those sinking motions around Antarctica, where water sinks down to great depth, down to 4 or 5 kilometers below the sea surface, that seems to be slowing down with time. The water that sinks is becoming fresher, that is less salty and less dense. We know that in previous parts of the previous periods of the Earth's history, that changes in those sinking motions in the polar regions have been linked to changes in climate. We haven't seen changes in climate result yet from the changes in Southern Ocean currents, but it's moving in the direction that would drive the similar sorts of changes to those we've seen in the past. So the Southern Ocean is important for climate because it has these unique circulation features. And so if the Southern Ocean changed, it would be significant for us. And the evidence we have so far is that the Southern Ocean is changing. It's warming, and to greater depth and at a faster rate than the global ocean average. And it's also changing its salinity. The salinity changes are important for 2 reasons. One is that part of the salinity changes are being driven by more rainfall and snowfall than happened in the past. That's exactly the sort of signal that we expect to see as a result of global warming. That is, the areas that are dry, where there's more evaporation than precipitation, will get drier and saltier in the ocean. Places where there's more rainfall than evaporation will tend to get wetter or fresher in the ocean. And that's what we've been seeing over the last couple of decades, is that the salty areas of the surface ocean are getting saltier and the fresher areas are getting fresher. And we see that signal in the Southern Ocean. We also see those changes in salinity down deep, right along the seafloor. And that's giving us a hint about how the ocean's interacting with the ice sheet on Antarctica. As the ice spreads off the Antarctic continent into the sea, it starts to float and forms glacier tongues or ice shelves. Where that interacts with the ocean can either melt. If it's warm enough, it can melt the bottom of the ice, or it can actually freeze to the bottom of the ice. The evidence that we found for freshening around the edge of Antarctica is an indication that that melting process is happening more rapidly than it did in the past. And that's a result of the warming of the ocean, we believe. And part of what we're doing on this trip is trying to confirm that picture. That melting of glacial ice by a warmer ocean is important for sea level rise. For the floating part of ice, if that melts, it doesn't change the sea level, just like if you have a gin and tonic and the ice cubes melt, your glass doesn't overflow. The floating ice is the same way. But once we remove or thin the floating ice around the edge of Antarctica, more of the ice on the continent tends to spread into the sea. And that transfer of ice from the continent into the ocean does increase sea level rise. And our short satellite measurements over the last 10 years show that both Antarctica and Greenland are making larger and larger contributions to sea level rise as a result of melting around the edges. Yeah, I guess for me, in one sense, I feel incredibly lucky. I feel lucky that somebody wants to, that I can have a job where people will pay me to think about stuff that I think is really fascinating. And so part of what motivates me is just trying to figure out how the ocean works. And it's, when you're out here on a ship at sea surrounded by this vast expanse of ocean, it's amazing to think that we can actually understand it, that we can make measurements that help us understand why the ocean moves like it does and how it's changing and why it might be changing and what the impacts of those changes are. Another motivation is climate change. The ocean does play a critical role in the climate system, and one of the ways that we can really sort out whether climate's changing or not and how rapidly and why is by measurements of the ocean, because in the atmosphere the weather systems make the temperature and rainfall patterns change a lot from day to day, week to week, month to month. The ocean is a bit more steady, so it warms more gradually and it cools off more gradually. And that tends to smooth out a lot of the noise. So a lot of the signal of climate change is in many ways clearer in the ocean than it is anywhere else on the Earth. So, I think the evidence is growing. It's clear that climate change is happening now. What the role of scientists needs to be is to understand that well enough that we provide society with the information they need to make some decisions, because we have some really tough decisions to make. Each decision we make about how to slow down carbon emissions or how to respond to the challenges of climate change will have other implications for our economic and environmental and social systems. And we need the best information we can to be able to make sound decisions. And that's really what we're on about, I think, is trying to understand the climate system well enough and interpret the changes that we observe now well enough that we provide community with the information they need to make some sound choices.
Do you remember any one particular moment where you thought, yeah, this is what I want to do?
I grew up on the sea, and I grew up, my mother was a science teacher, and so we used to muck around in tide pools, and she'd bring microscopes home from school, and we'd look at whatever we could find in the pond water and stuff like that. So the idea of science as something that people did wasn't completely foreign to me. And then I started studying geology and realized that all seemed to move a little bit too slowly. And I love to be in the mountains, but I probably didn't want to spend my life studying them. and then started studying physics in a department that was all high energy physics, and that was all a bit too small and fast and didn't quite grab me. So the ocean was somehow in the middle. It was a field science. I could get out into the natural world and study how it was working. And I think I was probably caught up a little bit in a romantic notion of what it was like to go to sea. Nights like last night when we were rolling around like crazy and falling out of our bunks makes you realize that it's not always as romantic as you might have imagined. But it's been a good choice for me. I love it, so I keep coming back. I got grabbed by the Southern Ocean, I think, during graduate school. In my courses, we talk about different ocean currents around the world. And here's this current, this circumpolar current that circled around Antarctica, the largest current in the world ocean, and yet we didn't know how it worked. You know, the dynamical ideas that we had that explained most of the ocean circulation patterns at other latitudes didn't really work down here because of the unbroken channel of ocean. All the previous theories sort of needed an ocean basin on the right-hand side to support pressure forces that could then drive the currents and so on. But there was something missing in the Southern Ocean. We didn't really understand how it worked. And so it's been really exciting over the last 20 years or so to be part of a group of people from around the world that's beginning to fill in that picture. And now we do actually understand more or less how they work. Yeah, traditionally we've relied a lot on ships like this one. And there's still many measurements that we need to make that we can only make from a ship. And so it's a great tool, but it's also expensive and slow. So this trip that we're on now, it's a little bit like driving from Sydney to Perth at 20 k's an hour, and every 3 hours you have to stop for 3 hours. So it takes you a long time to get anywhere. So it's slow and it's expensive, and so there's a limit to how much of the ocean we can cover with if we only rely on ships. So over the last 5 or 7 years, we've started to develop tools that are really transforming how we do our work out here. One of those are Argo profiling floats. These are small cylinders that measure temperature and salinity as a function of depth in the ocean. We can toss those over the side, and they can change the buoyancy so they can either float or sink. And they drift for the ocean currents about 1 kilometer below the surface. And every 10 days they pop up to the surface, measures temperature and salinity as they rise, send that data back to us by satellite. And there are about 3,000 of those floats now around the world ocean. And in a real sense, it's the first time we're measuring the ocean beneath the sea surface. And in particular in places like the Southern Ocean, where shipping has always been scarce because it's a horrible place to be in a ship most of the time. So it's the strongest winds and the biggest waves anywhere you can find in the ocean. And there's very little merchant shipping down here. So we've always suffered from a lack of data in the Southern Ocean. These floats are allowing us to really measure the ocean for the first time in remote regions like this. And the third big one is satellites. So about 20 years ago, we started launching satellites that can measure a whole variety of properties of the ocean from space. The most powerful one for us as physical oceanographers who study ocean currents are satellite altimeters that can measure the height of the sea surface to within a few millimeters. And this is the height of the surface if you smoothed out all the waves. And so wherever there's an ocean current in the ocean, there's also a slope to the sea surface. So the sea surface sits about 1.5 meters higher south of Tasmania than it does against the coast of Antarctica. And we can measure those slopes of the sea surface really precisely with satellite measurements now. And that combination of satellites looking down from above and Argo floats profiling from below is really transformed how we do our work in the last 5 or 7 years. Yeah, so right now we're sitting at about 57 degrees, 24 minutes south. So we're about 2/3 of the way from Australia down to Antarctica. And we're right on the southern edge of this massive current, the Antarctic Circumpolar current. The current itself is made up of a series of streams or filaments that wiggle back and forth and look kind of turbulent, form eddies and meanders and a sort of complex pattern. We're right on the edge of one of those streams of flow right now. So an instrument in the hull that sends sound pulses down in the ocean is saying that there's about a 25 centimeter per second current to the south right here. So that's about half a knot to the south. The currents down here are not so strong compared to, say, strong tidal currents that people might be familiar with around the coast of Australia. but they're deep. They extend down to right to the seafloor, 4 or 5 kilometers below the surface, and they're reasonably broad, maybe 50 or 100 kilometers across, each one of these streams. So the band we're on right now is called the Southern Antarctic Circumpolar Current Front, technically speaking. But each one of these current jets is a boundary between warmer water to the north and colder water to the south. So at the moment, the sea surface temperature is about 3.5 degrees. Air temperature is about 2 degrees. And as we make our way north up to Frio, we'll see the temperature rise to about 16 or 18 degrees. And we'll do that in a series of jumps or steps, rapid changes of temperature over a short distance. And each one of those will be one of those current streams that make up the circumpolar current. In terms of the science, in terms of sorting out what's happening with the climate system and what the impacts of change are going to be, we've made really dramatic progress really in the last 5 or 10 years. And so that's a positive. It means that at least we know what we're doing, and we know what the impacts of that are going to be, so we have a better idea of what to expect if we do or don't act. A lot of the real action in the climate change issue at the moment is in some ways moving beyond the science. It's a social, political, moral, ethical, economic problem that's a major challenge for us. And the decisions we need to make need to take the best science into account, but there are many more aspects to it that need to be thought about. And to me, probably the most sobering thing is that probably the greatest impacts of climate change will happen to those who are have the least capacity to respond to it. In the sense of, I think it'll hit the poor more than it will hit the rich, and that'll happen both between nations and within nations. And so there is a moral and ethical dimension to the climate change issue. As scientists, it's not really my role to comment on that. I'm not an expert in that area. But what our role is to provide the best scientific knowledge we can so that people can make those tough decisions and avoid the worst consequences of climate change and adapt to the changes that we can't avoid.